we're going to talk about funky figures. And I think this is a fun topic. Some of them get pretty hard at times, but this is a topic that does not take a lot of sophisticated math. It takes more creativity. It's a little bit more puzzle oriented than usual. And let's take a look at some examples here. Pardon, I'm going to change a couple of settings before we get too far into this. Okay. So let's take a look at some funky areas here. Problem number 1. Oops. There we go. So we've got a square and we draw squares that kind of divide. Maybe we can call it a carpet. We divide the carpet up and we want to know just the area of the shaded L-shaped region. How do we find that area?
Don't go ahead.
That's fine, you can say it.
Okay, there are 2 ways we could do this. We could divide it up into 3 separate shapes, or we could find out the area of the non-shaded region.
Okay, we could divide it into 2 shapes or 3, either one. We'll go ahead and divide it into 3 there, and then how do we compute?
We know that the upper part of the L would be a 3x1 rectangle because of the dimension shown, and it'd be the same for the lower part. And since the square is a 1x1, it'd be a 1x1, so it's 3 + 1 + 1, which is 5. So this would be the area would be 5 squared, 5 units squared. 7. I'm sorry.
That's all right.
My math is wrong.
All right. So how about part B? What would be the way to do this without chopping this thing up into pieces?
We could find the area of the simple shapes, like we have a 3x3 square.
Keep going.
And then we subtract. So if we know the total, then we can subtract to find. So that is I think the blue square is, yeah.
Yeah, we can subtract, we can start with the big piece, big blue square, and then we can subtract out a square that we cut out of it. Okay, let's take a look at number 2.
Yeah, this one we could also divide into simpler pieces.
Okay.
Hello. Okay.
And how do we do that?
May I try?
Yeah, go ahead.
So they divided part of it into different bars from 9 to 18. So we can see that they are equal.
Sorry, you're breaking up on me.
What each bar, so that each bar is 1.5.
Okay,
So
we can find the area of each bar. I think we can do this even more simply.
you can see that the 6 by 18 rectangle is half of the whole rectangle. And then the 9 by 6 is quarter of the whole thing. So then it becomes quarter times 2 out of 6.
I like this. Yeah, we can use, simple fractions to make our arithmetic easier here. And what are the two simple fractions together when we multiply them?
One over 12.
1 over 12. And that means that we can cancel that with one of our dimensions and quickly get an answer of just 18. Okay, so a lesson here is tiling. If you can take a surface and you can see that it is tiled by some kind of a small unit, then you can much more easily get a grip on how to compute the area one way or another. Okay, number 3.
Okay. This one, we could, since we know that each side length is 8, and the base of each like shaded triangle is going to be 2, because there are 4 of them. So we know that the area of each triangle is 2 units squared.
Okay, we can do it by finding the area of each small triangle. Is there a second path?
Of course.
What's our second path?
We could find the area of the non-shaded triangles.
That's a possibility. We could find the area of the non-shaded triangles. I'm thinking of something a little bit different.
We could try and find the area of the entire triangle and subtract the number of shaded triangles with a percentage.
Yeah, we have 10 shaded and 6 non-shaded. And in fact, the number of shaded triangles, so we can first compute the area of the whole thing. And then we can multiply that by the proportion of the shaded triangles. But notice that the shaded triangles, the total number of them is T4. What's the total number of triangles, shaded and non-shaded? By the way, that is the 4th triangular number. And I'm keeping it that way for a reason for the moment.
That mean it's T5 plus 1.
Say that again for me. The total number of triangles, shaded and non-shaded, is what?
Would that be T5 plus 1?
Oh, it is. I'm looking at it differently, though. There are T4 shaded triangles. How many unshaded triangles are there?
T3.
T3. So we could say T4 plus T3, but that simplifies. And we didn't talk, this is a good moment. We didn't talk about the simplification previously, but if we take 2 consecutive triangular numbers and add them together, what happens?
You get another triangular number.
Not another triangular number.
Oh, you get a
You get a whole triangle.
You get a square.
You can make a square.
We get a perfect square. We do. So we could say this is 1/2 times 8 squared times, and T4 is going to be 4 times 5 over 2. And then the square number is going to be 4 squared. And I like this because we can cancel and get 2 squared remaining right there. And we can cancel and get just 2 to 1 power. And then we can cancel that last 2 here. And we just have 4 times 5, which is 20. And, you know, this is way too elaborate. You know, this isn't something that we necessarily needed to do. I just kind of wanted to point this solution out because every time you learn something in mathematics, there's a chance that it fits into something that you can do to solve another problem. And it's a little example, but it's a fun little example.
Please, could you go up once?
What's that?
Please, can you just show your work properly? Like, can you bring it down?
Oh, this right here?
No, not this one. For question 3.
Like that?
Thank you. Yes.
And I will post both these documents once we're done with class. I've also got another document that's in the works that's going to have a little over 20 practice problems, and I'll post that later today after class. Well, let's take a look at number 4 now.
I think we could begin by giving the width value. We could give the width a value of 1.
I like this. Let's create our own unit. 1, 1, 1, 1, 1, 6. Okay. Now what?
We can divide the shaded areas into small squares, like each having like the area of 1, because 1 times 1.
That's true. We could divide the whole grid into a big 6 by 6 grid.
Yes, please.
And then we can
just count the number of squares.
We can. What's another path?
You could make it a 6 by 6 square. Then to find the bigger shaded area, you subtract the smaller square from the bigger one.
Every time we subtract a smaller square from a bigger square, we get a leftover shaded part. Kind of express this algebraically like that. And so what that means is that we're going to have 6 squared minus 5 squared for the big bent shape, and then 4 squared minus 3 squared, and then 2 squared minus 1 squared. And do we see anything that we can do within these numbers? I know you can all compute them, and that's fine, but we're going to look for all the patterns we can find here. What's another way to think of 6 squared minus 5 squared?
That would get you a triangular number. No, it wouldn't.
It's not a triangular number. Look at it on its own. What's another way to write x squared minus y squared?
Oh, the difference of squares. It'd be x plus y, x minus y.
Okay, does anything interesting happen after that?
all the ones that have a minus like 6 minus 5 is 1. So it's basically the same thing.
Which is our sixth triangular number, which is 6 times 7 divided by 2. And we have 21, but that wasn't quite what we were doing. We're asked to find the fraction of the square shaded region, which is then T6 over S6. And again, we see that computation with a triangular number and a square number, which allows us to do a little bit of canceling before we finish our computation. Okay, moving on to number 5. Oh, has anybody here ever played with Tangrams?
No.
So Tangrams, and I'll write this out here in case you want to look this up somewhere on the internet. Tangrams are an old Chinese puzzle, and there's a story that goes along with it, which is that the square was whole, and then it was dropped and broken into these pieces, and it's actually hard the first time you ever do it to arrange them back into a square. And some people make other tangram puzzles, like take the pieces and arrange it into, some rectangle or some, elaborate picture like a chicken or something like that. Anyway, those can be good, mind puzzles. But here, we want to know the ratio of the shaded square to the whole big square. How do we do that?
I'm not so sure as to how to start, but I know that each of the triangles is a right angle triangle. Let's isosceles.
That's a good observation. That helps.
We could start by giving our own unit.
Perhaps we can start with units. I'm gonna let us go a little further. So we don't need like a unit of length, but we talked earlier about units of tiles.
Yeah, so we could.
Well, I've noticed that when looking at it, the side at which the black triangle is in falls within 1/4 of the square.
Yeah, if we kind of continue this down, we see that more easily. That's true. Okay.
Yeah, so since
And then
the
the
black
two
part is
triangles
square,
which are what?
the other two triangles form another square. So the black part is half of that quarter, giving you 1 out of 8.
That's true. We can divide this up ultimately into 4 little triangles, and we have 2 out of 1/4 out of 1/4, giving us 1/8 of the total big square. Very good. Okay, how about number 6?
we could find the total area and then do 3/16 of it.
Possibly.
And then we could add all and then subtract from the total. Add all of the 3/16.
But you see that the L shape are 3 squares that have been put together to form an L, meaning one of those would be 1 out of 16.
Oh, so you're chopping this up into pieces like that are 1/16 each?
Yes.
Seems like a good plan.
So, okay, let me go through this.
I have another idea.
Please, I have a solution, I think.
Okay,
But since
Mamba.
it's a square, it means it's 1 out of 4 times 1 out of 4.
Yeah, each of these is 1/4 the side length of the hole. And then we have 2 of them making 1/2 the side length of the hole. And so we get 50 as the answer. So that's one solution. Here's another possibility is we say, hey, 3/16 times 4 is 3/4. So the center square must have 1 minus that, 1/4 of the area of the whole big square. And so its side length needs to be half, so that a half times a half is a fourth. So multiple ways we could do this one. We could subtract the little square from the big square. Think about it that way. Or we could divide things up into little square units. Okay, number 7.
You could divide this into a square in the middle and then 4 rectangles around it.
Oh, I like that. Let me copy that one. We'll do this in more than one way. Oh, I should copy the whole problem. Okay, so you want to turn this into a square with added pieces around it?
Yes.
I like it. That's pretty simple. And then what is the area that you get when you do?
So the square in the middle would be, the side of that square would be 2 plus 4 plus 2, which is 8. So the area of that square would be 8 squared.
I concur.
And then the sides would each be 4
8.
squared.
4 by 2.
They're each 4 by 2, so they're each 8 also. And in total, we get 96. I like that solution. Anybody else have another one?
I thought of just separating them into small boxes, each of an area of 4.
We could also tile.
Yes.
We'll call that solution 2. There's still another one that we could try.
I realized that when we divided the figure into 4, it was in an ascending order, so 1 square, 2 square, and 3 squares.
Yeah,
I was
tiling is definitely a good solution, and we could tile in multiple ways, but check this out. What can we do now?
we can find the area of the of the little of this stuff, and then remove it from 12 squared.
Yeah, what are the little L's?
6. No.
I think the little L's are 12.
Yep.
They're 3 little 2x2 squares, and this will give us
Oh,
the same total of 96 when we're done. So, and by the way, I have a name for this. I call this a big picture solution. Whenever you can see the image that you're looking at as a piece of a bigger picture, then you have the opportunity, one possibility of starting with the bigger picture. So if you ever hear me say that as we go through geometry over the next 3 weeks, here's a bigger picture solution. That's what I mean. Okay, number 8.
Well, for number 8, the total length of the sides of the structure is 8. And then we have the total length of the other side as 10. So then the first rectangle will have the first rectangle would have the edge as a length of 2. So then we can fill in the sides, and then we'll get closer to solving the question.
Could I give a suggestion?
Sure, what's your suggestion?
We could chop this up into 2 rectangles, because if we shift the 2x10 rectangle a bit to the left, you'll get a 2x7 rectangle, and then the next rectangle would be a 3x8 rectangle.
I see. You want to move the strips until they're in better position. I like that idea. And in fact, we can move both of them if we want. All right, we could take this right here, and we could move the 2x10 strip up here, and then the 3x8 strip right there. I like it. Now how do we compute?
So okay, from what you have drawn, you could divide into 2 rectangles, which would be 2x10 plus 3x6.
Well, we could divide it up into little rectangles, or we could do what?
We could subtract from the bigger picture, which it would be, yeah, we just yeah, that would be 5 times 7, 5 times 8.
Let's see, we've got dimensions of 3, 10, and 8, 2.
My bad. It would be 6 times 7.
Okay. And I like this a lot because it's not even what I was thinking. So the purpose of this problem was to introduce the overlap. And this is kind of like what you've been doing with Wendy, correcting for overcounting. We could overcompute the area. We could start by just saying, look, we have two overlapping black strips. And those two overlapping black strips have dimensions 2 by 10 and 8 by 3. And now we can subtract the red portion in the middle, which is what?
3 by 2.
That's right.
2 by 3.
And once again, we got the same answer as before. It's always nice to work a problem in two different ways so that you have confidence that you've got the right solution. So yeah, you can always subtract away something that you've added twice. Okay, number 9. Has everyone seen those tick marks before?
Yeah.
Yes.
Yeah, just in case, if I put one tick mark on two segments, that means they're of equal length. If I put two tick marks on two segments, they're of equal length, but it may be a different equal length than the one tick mark segments. We're given the area of the whole big rectangle. And now we want the area of the triangle in the middle. What can we do, Shreya? Or somebody else?
I think one of the first things that we could do is we could try to figure out the side lengths so that it help us solve it.
So that's a possibility, but here's the thing. There's no definite side lengths here. Maybe this is a 6 by 12 rectangle. Maybe it's a 7.2 by 10 or an 8 by 9.
I think it can't be. I think it's better if we. I think we can choose our own side lengths, and that would help us.
So I like this suggestion, and this suggestion has a name. We can pick our own special case. This solution is called special casing, and we see it in a number of areas of mathematics, but I think we see it most often in geometry. That's where it seems to be most helpful to me. Is we may have a general figure, but we say, well, if all of the answers are going to be the same, then we might as well pick our own numbers. Maybe we'll pick numbers that are easy for us, like 6 by 12. I picked those because they're both even numbers, and so we can divide them by 2 with the midpoints. Great. What's our answer going to be in this special case? Or how can we find a way through?
We could look at the bigger picture.
I like it.
So we can find the area of the 3 triangles.
Yeah.
So first triangle will be 6 by 6, half of 36.
Okay.
I have a question.
Yeah.
Is if we were to use 6 and 12 as the things, and then the midpoint of DC would be the same length as AD, if you understand what I'm trying to say.
The midpoint of BC is across from the midpoint of AD?
Or no, I mean, if we are to use AD as 6 and DC as 12, the midpoint of DC would be 6, which
Oh.
should be as long as AD.
Like 6 and 6, 3 and 3?
Yes.
Right.
Okay. That's correct.
I think what he's trying to
I
say
think
was
he's
that
trying
he
to-
made a mistake to write 6 by 12 minus half 6, 6. Shouldn't rather be 6 by 6 minus that.
Well, that 6 by 6 triangle was this one right here. Did I not do that correctly?
Yeah, I'm saying in the what you wrote, right below special case, wrote 6 by 12 instead of 6 by 6.
No, it's 6 by 12 because that's the total area, and then we're gonna subtract the 3 triangles to get the gray triangle.
Yeah, we're going to subtract the 3 green to get the gray. And somebody help me finish computing the areas of the green triangles.
Oh, 13, 9, and
One of them was a
13.
6 by 6 triangle.
Mhm.
And then
So,
One of them is
6 by 3.
6 by 3, and the other is a 12 by 3.
3 by 12. It's 3 by 12.
Yep. 3 by 12 or 12 by 3. Okay, good. Now we can compute.
So wouldn't that be 6 by 12 minus 18 minus 9 minus 12?
The last one's not 12.
One is
18.
18.
Sorry, 18. I meant 18.
So I got 28.
Close.
27. 27.
27.
My bad. Sorry.
And one nice check on that is everything is a multiple of 3. So our final answer needs to be a multiple of 3. So good. We have this idea of special casing. Anybody else have a second possible idea with this one?
I was thinking maybe we can use the Pythagorean theorem to find out like since the hypothesis, the hypotenuse of each green triangle is a side of the gray triangle. We can find out every side and find the area.
Okay, now technically there's a way to find the area of a triangle given its 3 sides. I'm going to suggest that that's usually going to be ugly. And non-orally, yeah, it's fine to type here. I've got the chat box up now. It's usually going to be ugly to find the area of a triangle that way. So this would be Pythagorean theorem and then plus something that we call Heron's formula. Heron's formula, and we'll cover that sometime over the next few days. We're going to figure out why Heron's formula works. We're going to derive it and figure out the formula, but it's not easy to apply when you have ugly square roots. You can do it, and I've done it before, and sometimes you just have to, or sometimes it's the best way, but it's rarely the best way. So I'm going to keep that up as a possible path towards solution, but I'm going to suggest we do something else. I'm going to suggest we start with the whole big picture and then think of the green triangles as proportions of the larger rectangle. And so instead of computing all 4 of those like we did in the special case solution, we don't even need a special case because each one of them can be found as a proportion of the large rectangle. We start with the whole rectangle, and then we subtract off each triangle. And the first one of those triangles has area 1/2 times 1 times 1/2 of the big. And the reason is because it has the same width, but 1/2 of the length of the rectangle. And then of course we multiply it by 1/2. So if, W and L, and maybe we should just do it like that. Maybe I should just say 1/2 times, I'll factor it out later, minus 1/2 times W times 1/2 of L. And then the little triangle has half the width and half the length. And then the other medium-sized triangle has 1/2 the width and all of the length. And width times length equals 72. Maybe I should have just done that. Should have just said WL. And then we have WL, we can factor everything. 1 minus 1/4 minus 1/8 minus 1/4. So in total, we have 3/8 width times length. And we're told that's 72, so 3/8 of 72. So I'm going to call this solution proportions or proportionality. Any questions about this one? It's fun kind of seeing how many different methods there are for doing this. You see all these different methods, and suddenly you can see, any one of them applying to different geometry problems that you might be tackling, whether you're trying to find the area or do something else ultimately. And you'll notice that I have solutions to all these problems. You can go back and look at them and walk through the different techniques. I think we've talked about even more techniques than I included here. And so now we're going to do some types of these that are a little bit tougher. We're going to include circles in particular, curved stuff. And what are we doing here? Oh, wait a minute. Do we have enough information? Did I miss something? Oh, yeah. We do have, it has radius 3 inches.
Could we start by finding the area of the bigger circle?
That seems very reasonable. How do we find that?
Well, the diameter of the smaller circle is the radius of the bigger one.
I agree. So what's the area of the bigger circle?
Since area is pi r squared, that would be pi, the radius would be 6, so that would be pi 6 squared.
36 pi.
Okay. So now I'm going to challenge you all. How do we know that pi r squared is the formula for the area of a circle? How do we come up with that? It's kind of a funny question. The first time we hear that formula, you know, we really have no idea how that was derived. Now, when you get to calculus, calculus is going to be a tool that allows you to find a solution for this pretty easily. But we don't yet have calculus. We're going to do something, though, that is a little bit like calculus. If we take a circle, and you know what we want to do, we know how to compute the area of a rectangle, right? That's sort of like our fundamental basis of thinking about area, is thinking about it in terms of, you know, like little unit squares. How many total little unit squares could we make out of some, you know, picture, rectangle, cut it in half to make a triangle? We kind of, you know, compare everything to little unit squares in some way. Rectangles, you know, length times width, that's the easiest. Can we turn a circle into a rectangular-ish shape? I mean, we could like squash it and move it around, but we might not know what the dimensions look like, right? You know, we could divide this circle up into any number of little shards. Do you know what we call those? Each one of those is called a sector. And you've probably heard that word before. Sometimes if you have like a radar screen or any kind of a circular map, people talk about sectors of the map. That's a sector right there. We're going to take those sectors, and here, maybe I've chopped this up. Imagine I've chopped the whole thing up into like 16. Yeah, 16 little shards, 16 sectors that make up the whole circle. I'm going to take those and rearrange them. Until we have something that is close to rectangular shape. Now, somebody tell me approximately how tall or how wide is this shape?
The radius of the circle.
Yeah, this is approximately as wide as the radius. Now, how long is it?
The circumference divided by.
Yeah, it's about half the circumference long. And what do we know about the circumference of a circle?
It's pi times the diameter.
Yeah, by definition, the ratio of the circumference to the diameter is pi. So C equals d pi, and the diameter is twice the radius. So we have 2r pi. Oops. Excuse me. So half of that is r times pi. And if we multiply length times width, we get r squared pi. And of course, this is not exactly true, right? Like, you know, this right here, it doesn't form a perfect rectangle. It kind of goes down and dips in to these pieces right here. But the finer we chop these sectors up, the more of them that we use, the closer and closer it gets to an r by r times pi rectangle. And so this does approximate the area. And when you get to more advanced math like calculus, you'll see that you can make this rigorous if you want. Okay, moving on. Number 2. Well, this one's tougher. That's a funny shape. I don't remember learning a formula for that shape. I'm going to let all of you chew on this one. If you finish it, you can think about number 3. I'm going to refresh my drink while you think. So any ideas about how we can think about this strange region in the middle of this triangle?
We could think of those 3 segments as we could think of them as segments of the circle that are tangent to each other.
Okay, we can think sectors. That's the word you're looking for.
My bad, sorry.
That's okay. And a segment is something different. I'm going to go ahead and mention this since we brought up the word sector before. Let's take a look at what a segment is. If we start with a sector like that and cut off the triangular part, that little shaded piece right there is what we call a segment. And maybe one way to remember that that's a segment is sometimes we say that insects have segmented bodies. So you can think of a segment as something that's sort of like cut off as its own piece from the whole. And then a sector is, you know, is the piece before we cut off the triangle. So segment, part of a sector. But yeah, we have this triangle and we have sectors of some circles. We don't see the whole circles, but we can use our big picture thinking if we want. Okay, I won't draw the others, but you know, we could, or I won't draw them all, but we could think of the same thing going on. We can have 3 circles, one centered at each one of the vertices of the triangle. By the way, does anybody here know how to find the area of an equilateral triangle? Maybe we need to step aside here.
Got the formula.
So some of you know a formula. Well, whether or not you know a formula, we're going to derive it. Let's say that we have an equilateral triangle And I'll go ahead and say side length 6. We'll generalize later. Now, what we know is that the area of a triangle is base times height divided by 2, right? So we want some way to compute base times height over 2. Well, we have the base already. So it's going to be 6 times the height divided by 2. And we need the height now. How do we find that height?
Pythagorean theorem.
If we drop that altitude, by symmetry, we're dividing the base into 2 pieces. You could say by symmetry, or you could say we've got 60 degrees, 60 degrees, and we have 2 angles and a side in between that are the same. And we haven't talked about this yet, but we're going to find that that is enough for congruence, 2 angles and a side. So we know those 2 triangles are congruent. So we know that, that their bases are the same. Okay. In fact, we have more than that. I think we had 2 angles and 2 sides, but so the third sides must be the same as well. So those are both 3. And now we can apply the Pythagorean theorem to this green triangle right here. We can say h squared plus 3 squared equals 6 squared. (36 minus 9 is 27. So h is the square root of 27, which is 3 root 3. Now we can say 6 times 3 root 3 divided by 2, and we get 9 root 3 in total. But this is something we can generalize. If we wanted to, we could start with side length s and make each of these s over 2. And base times height over 2. Well, let's see. We need the height. Height squared plus s over 2 squared equals s squared. Pythagorean theorem on the red triangle. So h squared is s squared minus s over 2 squared is s squared over 4. And that's 3/4 s squared. And the square root of 3/4 is root 3 over 2. So we get that root 3 over 2, and that's pretty common. We see that in our 30, 60, 90 right triangles, which is what we've got. Our equilateral triangle is 2 30, 60, 90 right triangles flapped together. And then we get base times height over 2, which is s times root 3 over 2s, all divided by 2. And that gives us a formula. S squared root 3 over 4. So some of you knew this formula already. For those of you who didn't, you have it now, but most importantly, you know how to derive it. If you ever forget, you can always just, walk through the same computations here. So let's go back up. So now we want to know the number of square meters in the area of the region. And so somebody tell me, what are the computations we're going to apply to this now?
So we're going to have to compute the area of the main quadrilateral triangle using the same method as we did below, and then afterwards we need to find the area of each of the sectors of the circles used to form this equilateral triangle and subtract to give us the area in the middle.
I totally agree. So now the area of the big triangle is? How do we apply the formula that we just derived?
That'll be 4 root 3 over 4.
Goes root 3.
It does simplify to root 3. Minus.
That would be since the angle for each sector would be 60 degrees times 3 would be 180, which is half a square. Sorry, a circle. So that would just be half times 2 pi r, which would be pi r.
What's our radius?
1 meter.
Right. So the area of a whole unit circle would be 1 squared pi. Yeah, our answer is just root 3 minus 1/2 pi. And if you're not used to seeing areas that funky with multiple irrational numbers involved, you're going to see that more and more. That's going to pop up a lot in geometry. And we see exactly where it comes from, so we don't have to worry too much. Okay, let's keep moving. How about number 3?
Could we divide the shaded region into, that'll be 4 right angle triangles and 1 rectangle?
Let's see, 4 right. I see what you're doing. Oh wait, do I?
You could
I'm not
just
very sure.
draw
Okay.
the squares.
I'm going
over.
to copy this one onto another page because
Yeah,
I think we're going to have multiple different paths forward between us. Okay, I think I know what the first person was suggesting. Like this?
No. Well, in my mind, I thought he meant like just
Yeah.
squares over it. So you'd have a cross on 2 sides.
Okay, I see non-Norley suggesting chopping things up into little triangles. There are multiple ways to do this.
Like that. That's what I meant.
And this is the one you wanted to do too. This came to mind most easily for me as well, though there's multiple ways to do it. The first way could be done. I think the computations are more difficult because maybe the side links are more difficult. But here, I like this partially because we can continue on with a tiling method. We could just chop, any square here, and we're kind of, this is composed of 5 of these squares, each of side length 1. But we can see how many different shaded little triangles do we have?
10.
10 in total. The middle one has 6. We can see we're missing 2, and then we've got 4 extra. So we've got 10 of these little triangles, and what is the area of each of those 10 little triangles?
1/8. 10/8 by 4.
Yeah. Actually, I'm gonna erase the second one. I don't think that we need this second solution. Okay. I accidentally got a problem on 2 pages at once. Let's put it together. Okay. Now I'm going to give you all a few minutes for this one. Everybody try to do this on your own with your own paper. Harshita, can you hear us? Pull out some paper. Let's try to work on this one. Pull out some paper. Try to work on this one. I think Harshita's talking to her brother or family member.
I think I've got it.
Okay, hold on to your answer for a moment. I want everybody to have a little more time on this one because this is a little bit tougher than most of the problems that we've worked. So non-Norley has a suggestion that is close to what we need to do, but not quite. So you can find the area of the shaded portion and take the square root of it to get the side length. He's thinking partially correctly. if the shaded region is 5/9 of the area, what else do we know?
Would it help to know the actual value of the shaded region?
Maybe. I don't think that we have to do that much work. If we're clever, we can do this without doing much computation at all.
Yeah.
Yeah.
Now, whenever it is that we have two things that fit together, if we know one, we know the other. If we know one, we know the whole, we know the other. The shaded region is 5/9 of the area. The non-shaded region is 4/9 of the area. And so we have the opportunity to focus on either one. What could we do with the non-shaded regions?
We could divide them into 4 pieces, but I'm not so sure because that's not exactly what I did. So,
Anybody else have a suggestion as to what we could do with the non-shaded pieces? Non-Norley says we could find their area. That's true. We can find the area of the big square. We can find the area of the non-shaded region, but I don't even think we have to do that much work.
We have to find the sides of the non-shaded area. Like,
Do we have to find the sides? We could.
The sides are given though.
but doesn't that mean that the ratio of the shaded portion to the total area will be 5:9? So you can just assume that the total area is 9. And for a square's area to be 9, wouldn't its side have to be 3?
Sure. But we're told that AB equals 5. We're told that the side length is 5. And you're thinking in a way that is part of what I'm thinking. And this will become more clear when we find the right way to fit the pieces together. What is the non-shaded area?
Total of like the total area of the non-shaded area.
No, I mean in description. What are those little pieces?
Oh.
I mean, each of them is a triangle.
Yeah, it's a right angle.
Right triangle.
Yeah.
Keep going. Keep describing.
It's isosceles.
We have 2 isosceles right triangles, and they're congruent to each other. What can we do with them?
form a square.
They form a square. Let's do that. Let's move one of them into position so that the 2 of them are together down in that corner. And then we see that shaded area is 5/9 and the unshaded area is 4/9. How does that help us?
Well, 9 is 3 squared and then 4 is 2 squared. So I have
That's
a
right.
feeling that they have something to do with it.
Yeah, a green square it has area 4/9 s squared, where s is the side length of the square. And yes, I know they gave us the side length, but it doesn't even really need to be part of our thinking until the end. If the area of that green square is 4/9 s squared, what is its side length?
2/3.
2/3 of s. So what is that length right there?
1/3 of s.
That's right. And since s is 5, our answer is simply 5/3. Very little computation necessary. And this happens a lot in problem solving. If you do most of your work on the thinking side, you have to do far less on the computation side.
But with my method, I just divide it into tiles.
You divided it?
Tiles. Divided it into tiles.
Yeah, and we can divide this into tiles, and that's totally fine. We can divide this problem into tiles, and it's just like some that we've done, but we have to go through 3 or 4 steps, to go between, we go length to area into tiles, and then back into lengths again. And my focus was on getting you to see it basically all in simple, straightforward steps without any kind of computation in between. No chance to make a mistake. Best chance to sort of generalize the process. Okay. And now we get to the circular segments. We've talked about this, but now let's find the area of one. How do we find the area of that little piece that's cut off?
I'm not so sure, but I'd say you'd find the area of that as a sector. Then you subtract the triangle inside from it.
Good. Okay. Now we take the area of the whole sector. And I like to write this out kind of algebraically. That minus the triangle that we cut off. I don't know if I did that well or not. Oops. Quarter of a circle minus an isosceles right triangle. Yeah, that's better than these. Okay, what's the area of the quarter circle?
pi.
And what's the area of the isosceles right triangle?
32.
How much?
32.
32. And we get 16 pi minus 32. Yeah, the segment itself is hard to turn into anything, but we can see it as a piece of a bigger picture and subtract away what we don't want. Good. So how about one where we have a 60-degree sector?
So then you'd have to find the area of the sector using the angle. So that would be 60 out of 360 times pi r squared.
Good. So once again, we have a sector that is equal, a segment that is equal to a sector minus triangle, and the sector, its proportion of the circle is 60 out of 360. And so we take that fraction of the area of the circle, and then we subtract. What type of triangle is that in the middle?
Equilateral.
Equilateral.
It's an equilateral triangle, so we can apply the formula that we derived just a little while ago. And in total, we wind up with 6 pi minus 9 root 3. Any questions or thoughts about this one? Okay. Let's take a look at number 3. Uh-oh. Problems 3 and 4 got kind of smushed together. So we'll break this up here. I didn't realize that I was resizing one of my lessons when I put it together. I think it's because I changed the font size. Wait a minute. Oh, I think it's actually the second diagram that goes with problem 3. So my apologies if that's not clear in the document. Maybe I'll go fix that document and repost it later, but I think I'd rather spend time on the homework problems that I'm going to leave you. Okay, so right here, what do we do? What is this thing? And I know what you're thinking. You're thinking it's a flying saucer and aliens are coming for us. But what can we do with the flying saucer?
Well, it says that the radius of the triangle of the circle is 6, and the distance from D to E is also 6. So that means that they join at a 60-degree angle. I'm not so sure how for my words, but they join with 60 degrees, connecting D and E to the centers of circle.
Very good. You spotted an equilateral triangle. And so we know that we've got 60 degrees all around. Why does that matter?
So we just do what we did in the first one, multiply by 2, since it's half of the segment if you use the first one.
Very good. So we are looking for 2 times the area of a segment, which is 2 times sector minus triangle. Okay, and what's the area? Oh, this is actually the same size as the previous problem. So we just take this and multiply it by 2. We've already done our computations for this one essentially. And our area should be 12 pi minus 18 root 3. Good. Okay, yeah, you're going to see those flying saucer pieces fairly often because circles are just so common. Intersecting circles are a perfectly reasonable thing to study. All right. Now this one's a little funny.
So I see there are 2 segments over there, and
Okay.
and the triangle divides the circle into half. And we know that the diameter is 12 because of the triangle.
That's true.
And if we join from the center down, we can make an equilateral triangle.
Perhaps. Do we need to do that?
So we could find the area of the segment.
Okay, we've got these two segments. And you know what? They happen to be the same size as in the previous problems. So we've already got our computations there. What is it that we need to do?
By 2, and then we write in the form given and add the
Yeah, all we need to do is add the area of that extra semicircle. So what's our final answer going to be? First, what's our area? Let's find that. Let's not bother with the way the problem's asked. That's probably for easy checking for a contest problem. What's our total area?
the semicircle is 18 pi. So when we add that to 12 pi minus 18 root 3, we get 30 pi minus 18 root 3.
Yeah, we just add this to our answer to the previous problem, and that's what we've got. Even though the segments are not arranged in the same way, they are the same segments. Good. Now one more here.
51.
That's right. Okay, let's take a look at number 5. What does that shaded region look like?
Flower.
It does look like a flower. And by the way, you will see these pieces on this flower referred to as petals. So when you hear that, you'll know. I think it's kind of a casual reference. I think it's not quite as formal as segment. But what can we do here?
We could find the area of one segment and then multiply by 4.
Actually, you have to multiply by 8.
Four petals, and each petal is 2 segments. So we have 8 segments total. Oops. So what is the area of one of those segments? How many degrees in each segment?
90.
They are 90-degree segments.
I think it's 32 pi minus 64.
That sounds about right. I'm going to do something here. You know, when I look at this, I see the ability to rearrange 4 petals at a time such that we have 4 shaded petals around a square. And we have a radius of 4. And so the side length of the square is 4 root 2. Not that we really need that. We could just say, we could say we've got 4 of these little right triangles. And one way or another, we could take the area of any one of those circles, which is 4 squared pi, subtract the area of the square, or 4 little triangles in the middle, and multiply all that by 2. Did you say 32 pi minus 64?
Yes.
I thought so. That's what I get as well. And different ways to do it. If we wanted, we could compute each one of those segments individually. And individually, they have area 4 pi minus 8, and then we could multiply that by 8. But I just kind of thought, one more, kind of creative, move things around to make computation as easy as possible. It's also, it's really good to know 2 different ways to compute an area. It's good to know 2 ways to solve any problem, right? If you know 2 ways to solve a problem, then you can always check them against each other. And how many people here have never made a computational error? Like, that would be nobody, right? We all make mistakes. In fact, if you work lots of problems, and that's what you need to do to become a good creative problem solver, you have to just work hundreds and hundreds, thousands of problems eventually, thousands and thousands. Along the way, you're going to make lots of mistakes. Everybody does. But the more often you find 2 different ways, and we had that with a lot of problems today, the more often you find 2 different ways to work the same problem, the more often you are to catch errors in your thinking or your organization. And that's a lot of the way in which we become better, more accurate with our problem solving. And it helps us, it forces us to think things through a second time. So that is, I think that those are our last problems for funky figures. And I've got kind of a summary of different strategies and tactics that we use that you can read through later. Now I'm going to go ahead and introduce kind of a fun topic. We're not going to spend as much time focusing on it, but I want you to be aware of this topic because it's fun, and you can go through some of the exercises here. We don't have time to make this into a full class, but these are polyominoes, excuse me, up at the top here. And polyominoes are an area of recreational math. I guess you could call it recreational math, but it can be quite serious. Anything that you can define as a mathematical object and start to ask mathematical questions about is serious mathematics, but these are kind of fun. And I've got some names down here for the different types of polyominoes. And of course, probably all of you know about dominoes because there are all kinds of games that you can play with dominoes. Anybody ever set up dominoes to knock down in a long cascade?
Yeah, I used to do it all the time, like make different kind of stuff.
Yeah, it's fun to look on the internet for videos of gigantic domino rallies.
Yeah, 49 pictures and stuff.
Has anybody here ever played the game Tetris? Is that still popular? Okay.
I have.
Yes.
Yeah.
Yeah, Tetris is a game based on polyominoes. Most of the different shapes are what we call tetrominoes. So those are the ones with 4 squares total. And Tetris does include the triominoes, the dominoes, and the monomino. But it's mostly about the different tetrominoes. So I've just got an exploration here, and I'm going to leave this to you just to kind of work through as you like, and maybe ask your own questions. What would, after you see the ones that I present, what might you study about polyominoes? All right. We'll go ahead and conclude class here, and I'm going to work on getting out the problem set. It'll probably only take me about 20 or 30 minutes to have it ready, and then I'm going to post it on the site, and you can have that to practice over the next few days. Any questions or thoughts before we wrap it up? Okay, I'll see you all on Wednesday.
Thank you.
Okay, thank you, Mr. Crawford.
Thank you, Mr. Crawford.
You're welcome.
Thank you. Bye.